Hello, everyone.
Hey, Clément. How are you?
I'm okay. How are you?
Good. Edwin should be here shortly.
Where is he physically now?
Glasgow.
Let's go. Okay.
Yeah.
And so, if I read correctly, the creator of the white space programming language.
Yes. Yeah, it started as an April Fool's joke.
Yeah.
And then they had to make it real. Him and a student is it is. They end up writing an interpreter and everything.
It kind of sounds like an ignoble kind of idea where you try to work on something stupid and it ends up being interesting sometimes.
Yeah. Shoot him an email. So we've got about 34 additional people on YouTube. It says he's there now, but I think maybe I sent the wrong link. Let me send him a new link. Same link. Oh, yeah, no. Email. Seems the
Oh, this looks better. There's people here.
Yeah, sorry. I don't know. I feel like I see you the right one, but who knows? It's totally fine. Sorry about that.
Never mind.
Yeah.
No.
Like I said, these things always have a way of finding a way to make things more difficult.
It's interesting, isn't it, that even though you can't physically go to the wrong room, you can still somehow virtually go to the wrong room.
Yeah, exactly.
Yeah, I guess I should check my screen sharing.
Yeah, try that out and make sure
That's
it's
going to
good.
be kind of crucial to the whole exercise.
Yeah.
So, are we good?
Yeah. Flip through one just to see if it cut off or anything. Last time we had a bunch of ones that were cut off. Nah, it looks good.
And I've got a text editor buffer as well. Is that completely visible?
Yeah, it looks like it is. Yeah.
Okay, good. In that case, I'm all set whenever you are.
Yeah, I'll go ahead and start the show, and then you'll take it from there.
Sure.
So one thing, Edwin, feel free to take questions whenever. I have it's streaming on YouTube as well. We have like 45 people there. So
splendid.
I'll keep an eye on the YouTube channel for any questions that pop up there as well. It's very much like a seminar style. So
sure,
laid back. All right. So thanks everyone for coming to. I think this is the 12th colloquium this semester. And today we have the pleasure of having Dr. Edwin Brady, who is the chief architect behind the Idris programming language, and he'll be talking about that today. Currently, he is a lecturer in computer science at the University of St. Andrews, where he studies type theory, dependently typed functional programming, compilers, and metaprogramming. He's currently working on a new implementation of Idris. Idris 2, right?
Imaginatively enough, yes.
And he has several hobbies. He likes to play Go, I guess, and walking uphill and cricket. You do like cricket a lot, don't you? I think you tweeted a bunch about it.
I understand
about
cricket, but maybe now is not the time.
Yeah, I know absolutely nothing about it, so it seems interesting. Yeah, so today he's going to be telling us about dependent type-driven program synthesis. So thank you a lot, Edwin, for agreeing to come and give us this presentation.
Okay, we're all set then. Thanks for having me along. Yeah, so as Harley says, I work on the Idris programming language. I did a little bit of poking around the Augusta University website. I was trying to find what kind of expertise people in the group had. So I know that Harley in particular works on the Granule project. I don't really know to what extent people are familiar with dependently typed functional programming. So I am just going to blunder on with my talk, but I know that there's a relatively small number of people in the Zoom meeting, which means I'm hoping that interruptions will just work. And if you want to interrupt me, feel free just to interrupt me. And if that doesn't work, then I guess we'll try something else. So if I do make some assumptions about your background that turn out not to be correct, then please don't hesitate to interrupt. I'm going to assume, at least at the beginning, that you know a bit about functional programming, a bit about logic. This sort of thing will come up. So what is this talk going to be about? Well, certainly I'm going to tell you about my new implementation of Idris, but the thing that I'm most interested in working on at the minute is using Idris as kind of interactive program editor. So the general principle behind all this is that programming should not be a fight with the machine. You often get into the situation where you've got a problem you want to solve. You start writing your program, you write your first attempt at the program, you feed it to your compiler, and your compiler says no, because chances of you getting a program right first time very low indeed. And you get increasingly frustrated. You try a few things because the compiler's giving you error messages, but that's all the help it's giving you. So the principle I want to follow is that programming should not be a fight with the machine. It should be a collaboration with the machine. So I think of it as like a conversation. So I will give an initial suggestion of what the program is going to be about. It's like saying to the machine as my research assistant, this is the problem we're going to work on together. I'll write a partial program. The machine will guide me towards more of a working program. So the particular aspect of that I want to talk about here is program synthesis. So program synthesis, this seems to be quite a trendy topic at the minute. There's a lot of people working on program synthesis in a lot of settings, so particularly with Haskell and Liquid Haskell. And the goal of program synthesis is to start with a type and then generate a program that satisfies that type. In the context of programming as a conversation, I don't really want to give a type up front and have the machine give me an entire program. I don't want to essentially move the whole problem from writing a program to writing a type, because at that point I don't really feel like I've achieved anything. I'm just sort of kind of sweeping the dust under the carpet, that sort of thing. So I'm interested in being able to have the machine create fragments of programs. So if I have some particularly tricky subproblem, have the machine help me solve those subproblems. So, another thing to say up front is I'm new at this, as in I'm new at program synthesis. The ideas that I'm going to talk about today are things that I've kind of discovered by hacking around the IDRIS program synthesis system and learned about by reading various introductory things on type-driven program synthesis. It's entirely possible that there are things that I don't know about that you do know about, in which case, for me, that's half the point of giving talks, is that you can tell me about things that I should know about, and it'll help make the system better. So this is very much work in progress. I've got a number of examples to work through, but there's still lots of things that I think we can improve, and this is going to be what we do over the next little while. So what can it do? Why is it useful? And I'll talk a bit about how the version in IDRIS works. The key thing here is it's not magic. It's just it's an algorithm. I'm using algorithm in the traditional sense rather than the new media sense of heuristic. Right, so I'm going to dive into some examples. Just have several hundred examples here. As I say, don't forget to ask questions. Please interrupt. Please. Also, what happens if type questions. I like it when people say, what happens if you do such and such instead of the thing you tried, because maybe there's something that maybe there's something I haven't tried, and it'll be fun to find out together what happens. Okay. So I'll start with just introducing IDRIS program, introducing type-driven development. And IDRIS is a dependently typed programming language. So dependent types are, I prefer to say first-class types these days, by analogy with first-class functions. So types are first class and can be assigned to variables, can be passed to functions, can be returned from functions. So they're no different from other constructs in the language, like no different from an integer. So we'll see a lot of that happening as we go. These first couple of examples don't use don't use dependent types. They just use fairly conventional polymorphic types just to illustrate how things work. But we'll introduce a few more dependent types as we go. Now, the general idea behind type-driven development, as I said, start with a type and interactively build the program by refinement. So this first example, all it's doing is taking a number. So nat is a natural number, 0 or more, and a thing, a polymorphic thing. So in IDRIS, if you see a name starting with a lowercase letter in a type, that is a type level variable. So it's intended for familiarity for Haskell programmers. So way back when I started IDRIS, my target audience was luring Haskell programmers over to the dependent type side. So I tried to make it look a bit like Haskell. I haven't gone so far as having a double colon for types, so a single colon for types. Other than that, if you're familiar with Haskell, hopefully this is a bit familiar to you. So these just having a type is fine in IDRIS. This is an incomplete definition. It will compile. It will happily compile and run. It's just that if you encounter an undefined thing at runtime, you will get a runtime error. You'll also get a warning at compile time that your program is incomplete. But I think having incomplete programs is absolutely crucial in a modern programming language, because if you have an incomplete program, that suggests that if the compiler can work with incomplete programs, that's a place where a compiler can help you. Okay, so my text editor here will talk to the Idris compiler. So I've got an Idris menu. The first thing I could do is just add a clause. So if I say add clause, that takes the type and creates a candidate definition. So the simplest possible definition that would compile. The thing it's generated, so it's a function of 2 arguments. And this thing on the right-hand side, this is a whole. A whole, again, stands for a part of a program that hasn't been written yet. And we can inspect the types of holes. So we're going to see this sort of thing. We do see this sort of thing quite a bit when programming in Idris. So if you look at the type of a hole, you see the context and you see the expected return type. Another thing you can do, I'd like this in, I'd like this sort of thing in Haskell. I'd like a kind of interactive approach to programming. And I think there's a lot of tools in development that might help with this. I haven't yet found one that I'm confident enough to use in a class of 100 students and see that it's robust enough. But I'm hopeful that it won't be too long before there is such a thing. And so the sort of thing you might want to do is pattern match on some input. So we'll pattern match on this nat. A nat is either 0 or a successor. No, I haven't actually told you what this function is going to do yet, but you've maybe figured it out from the type and the name. What this function is intended to do is make a number of repetitions of this variable. So we're basically counting up to this number and giving copies of that variable up to that number. And I understand that you're very particular about counting in Georgia. So let's be very particular about counting here. So counting 0 copies of our thing, that will give us the empty list, and counting successor of k copies of our thing will give us, well, we'll take a thing and then we'll make k more copies of the thing. So 0 and successor here, that's our way of pattern matching on natural numbers. Okay, so far so good. We did that by pattern matching on the input, looking at the expected type on the right-hand side, and then just using a bit of our intuition and knowledge about how functional programming works, how writing this sort of function works, to make a definition. Thing is, though, what I just did there, that whole process of make a definition, split, put a well-typed right-hand side, is something I do over and over and over again. And as programmers, when we do things over and over and over again, well, we don't like that, do we? We like to abstract over the whole process. Or we like to, look for common characteristics of definitions and abstract over them. So essentially, what I did this summer was abstract over myself, make a reusable implementation of myself. And instead of going through that whole process, I could say generate definition, so with a cursor over rep, and it will generate me the first candidate definition for rep, which is pleasingly, it's exactly the same as the one I just wrote. So there is if you want to generate a definition from a type, what approach could you take? Well, you could start searching for all the programs. You could start searching for, or you could try to enumerate all of the well-typed programs, which is kind of what we do. We're building the programs incrementally. We're finding well-typed candidates, but then the question is, why did it pick this one? Why didn't it pick, for example, just returning the empty list? That would be a good thing to pick, because it would be well-typed. So I'll talk a bit more about the mechanics of how this works later on. But for now, essentially, the heuristic is it will generate a small batch of candidate definitions. So I've somewhat arbitrarily picked 16. It will generate the first 16 candidate definitions, and then it will go through those and order them according to uses of local variables. So it will try to use every local variable once. That's the basic idea. So in this case, it's making sure that it's using this nat and it's using this second argument. So the heuristic is based on the observation that if you gave the function an argument, chances are that function wants to use that argument. So we'll try to use that argument. Now, another thing though is that it won't always generate the definition that we want first time. So this doesn't free you from knowing what your program is supposed to do. So there's a sort of analogy here is, keep hitting it with a hammer, hit it with a hammer until you get the definition you want. So I don't actually have this in the menu yet. So this is a version of the editor mode that I've hacked up myself. So I can keep hitting this with a hammer and it will give me the next candidate definition. And see, it's giving increasingly unlikely definitions as we go. But if the first one finds isn't what you want, you can ask for more. Now I notice that Harley has unmuted himself. I wonder if that means there's a question coming.
Oh yeah, there was a question in the chat. I answered it for you. They were wondering if : was a built-in operator for append to lists.
Right, yeah. So I've essentially swapped the single and the double colon. So yes, thank you for answering in the chat.
Yeah.
Incidentally, I guess this is worth mentioning. The reason, well, there's two reasons for swapping it. One is just that colon has been used to mean type for longer and by more people than double colon. Which is, that's a reason. It's not a particularly great reason. But the other reason is I feel that I'm going to be using more type declarations than I am cons constructors, which is exactly the same reason as I understand it of why Haskell has the double colon for types and single colon for cons. But there you go. Okay, so let's leave that one there. So yeah, it's generating it just by a type-based search. Another example that I often use when introducing, or that I've that I try to avoid using, but often end up using anyway, is vectors. So vectors being, it's a classic example, a fairly tired example of a dependent type. It's lists that are indexed by their length, carry the length and the type, which means if you write a function over a vector, then the properties of the function will tell you about the length properties of what happened to the vectors. And one thing I've been doing with that is using it as an example of how dependent types help with your type-driven synthesis. And the interesting thing is with this new heuristic of try to use all the arguments exactly once, or as close as you can to once, so that's the ones that score highest. Then generating an append function, well, I'd say this is the append function. This is the append function you would expect. So that's the first one it finds by following the heuristic of trying to pattern match on everything, or trying to use everything. I mean, I can keep hitting it with the hammer, and it will give me again increasingly unlikely implementations of append, but the one we want is the one that comes out first. So it's kind of pleasing that this this is generated, so it's correcting it. It's kind of pleasing that this heuristic gives us a nice definition. Now, what I'd like to do before I go into how this works is just try to give you a feel for the sort of situations where this is useful to us. So in general, I like to use it's for freeing you from some of the burden of plumbing. So a lot of programming, a lot of functional programming particularly is about plumbing. So translating something from one type to another, or bind operators for monads, this sort of thing.
Yeah, Edwin, we have a question on YouTube if you don't mind.
Sure, why not?
So Dennis is asking, I'm wondering why rep, whose first argument is successor of k and then second argument is x, equals x appended to the recursive call. So they're talking about the step case from rep. Was chosen with the given heuristic instead of just calling the recursive call and not appending x to the beginning.
Oh, that's a great question.
Exactly once.
And that's because of the yeah, that's a really interesting question. I think it's because it doesn't find that implementation quickly enough. So the order it tries to find a result is look at the use the constructors, and only if the constructors don't work, then try making a recursive call, at least at the top level. So try making a recursive call once you've tried all of the constructors. So if I were to generate a bigger batch of candidates, then yes, that would absolutely be the first one it picked. So yeah, there's while I claim that this is an algorithm, there is no magic. There is still a certain amount of the magic numbers we pick will have some influence on the choices that get made. So I say it's an algorithm, that is, a human can explain what it does, but there are still some kind of magic constants that we've tweaked to get some better answers. But yeah, that's an interesting question, and I should probably look a bit deeper at that and think, well, maybe that is the first definition it should come up with, and maybe it would be better to. No, I've started thinking about that too much. I'll think about it after the talk, and I'll get back to the talk for now. But yeah, that's a really.
Can I ask you a quick question too?
Sure.
So, as I think I agree with you, functional programming is a lot about plumbing, but there's a lot of helper function, and I mean, quite often you write a small function to help you write a bigger function.
Right.
Does your algorithm like lookup, like when you try to define function number 2, does it say, well, maybe I should try to look function number 1 that you just defined? Or do you only use built-in constructors and functionalities?
Right. So it's it might be that as you make as you're building up a bigger software system, you're building up a collection of hints, essentially, so that the functions that you've written are hints that you might use for other functions that you're working on. So the internals of this system allow you to do that. The problem with adding hints is that you're also increasing the size of the search space.
Yeah, sure.
So I think we need some kind of way of some neat way of asking, search for a program, but guide it using a little bit of additional information that the programmer provides. And I'm not entirely against using machine learning based heuristics for this, because you might I'm not going to pretend I know anything at all about machine learning at the moment. Hopefully in a couple of months I will pretend that I know something about machine learning. But I sort of imagine a machine being able to say, well, usually in this sort of situation, other people use this helper function, so maybe that's the one you want to try exploring. So I don't quite know where the body of knowledge a machine learning system would get for that kind of system, but it's something I'd want to think about. But yeah, we absolutely need to be able to give the machine a bit more guidance than just blunder ahead with the constructors. Okay, just to give a couple of examples of what I mean by plumbing.
Sorry. Can I stop you again, please?
Yeah.
So I was wondering whether those menu commands that you just used are also available in the REPL as like commands.
All of them.
Not all of them. Okay, so
all of them are because it's an implementation detail of the Vim mode is that it actually works by talking to the REPL. It's a gigantic hack. So it talks to the REPL, pulls the response out of the REPL, and then puts it in the editor. So you can. This is also how it's tested. So the test suite does these generations via the REPL. But that's important that they work that way. Yeah.
Okay, I should then ask you later for where to look them up, because I don't at the moment know where they are.
Yeah, we should probably add something to the help that says, if you want some help on the interactive editing commands, here's where you go.
Yeah, that would be a good idea.
Yeah, more documentation is definitely necessary. Right. So let's talk about parametricity. So fans of parametricity know that if you are suitably parametric, then there are fewer implementations that can exist for your function. So I've got a few examples here that we would hope that program generation would be able to find just by, uncurry takes a function and takes a pair and applies the function to that pair. So let's generate uncurry. I don't actually like this implementation of uncurry it comes up with. I would prefer to do this just as a matter of taste. I would prefer to do this by pattern matching on X rather than projecting out the first and second components. So I'm just going to hit it with the hammer again, and yeah, that's the one I want. So yeah, if you're writing definitions that are suitably parametric, it's just about constructing, deconstructing pairs. Then we would hope that it would happily find an implementation. So everyone don't like that one either. That's a bit better. That'll do. So just a few examples. These examples, by the way, are borrowed from a GIN, which is a tool originally written by Leonard Augustin for Haskell. So it's taking advantage of parametricity to generate definitions that should be automatic, to be like immediate from the type. Let's look at one that's more about dependent types. So I'll explain a bit about what's going on in this implementation. So it's a kind of program that that you often end up writing in a dependently typed language if you're trying to use the type system to explain things about your data or relate to data structures. So a common thing to want to do in a dependently typed language is to express assumptions about the relationship between two structures in the type. So in this case, I've defined heterogeneous lists. So a heterogeneous list is a list where each element of the list could be a different type. In order for that to type check, we need to say that we need to say what the element types of the heterogeneous list is going to be. So it's indexed by a list of types. So if in the cons constructor here, if the first element has type T, then the index says that the first element has type T. So I should maybe have put an example. So you'll get types looking a bit like this, where I wonder if that type checks. Oh, that's a relief. So yeah, the H list, the index of the H list type says what the types of the elements are. So we can have lists where each element of the list is a different type. So if any dynamic type language fans tell you that you can't have lists with different types at each element, then firstly, that's not true, and secondly, I don't entirely know why you would want to do that if you weren't able to explain why they were also different element types. The sort of place where you might use an H list is with extensible records, that kind of thing. Anyway, it's not that I want to tell you what H lists are for, but I want to show you a thing that you often have to do with this sort of structure. Like you might have a predicate that says that extracts the element type at a particular position. So if you're doing some kind of lookup on an H list, you need to have a proof that the position or the element at position I has type tie in the type list ties. So the thing at position 0 has type T, because we know it's the whole list, the index of the list is T cons T, so the first thing has type T. And if the kth thing has type T, then the in list T's, then the k+1 thing has type T in a list that's one bigger. So if you look at this type, if you sort of period it the right way, you'll see that what we've done is essentially written the lookup function already. We've exactly explained that what it means to be the thing at position 0 and what it means to be a thing that's deeper in the list. It's a sort of prologue style encoding of a lookup function. And the fact that we've written this program once makes it kind of annoying that we have to write it again because just to keep the type checker happy. So this is one place where I quite regularly use program synthesis. Is just like I know that we should know what this program is supposed to look like. We've explained it in the type, so there we have it. So
one question in the chat, Edwin, is
yeah.
So one thing Christopher Leak noticed was that you're using the same symbol for cons for HList as in the built-in. Is it shadowing it?
Yeah. So the one you saw earlier isn't actually built in. It's in the library, but it's not. Idris is not. Idris isn't treating it specially. Or the only way in which it's treating it specially is that we've got this syntactic sugar. So we do tend to use a lot of different listy types, list-looking types. So I decided quite early on that it would be really useful to be able to overload constructor names, and because we don't worry too much about preserving type inference, because we give types up front. That means we can disambiguate which cons we mean by type checking. So obviously there's trade-offs there, and sometimes it is possible to grossly misuse this kind of feature. So please don't do that. But it's nice to be able to say, oh, we have a listy thing, so we'll just call it cons again. Yeah, so that's one of the details that I have a tendency to bypass if people don't pull me up on it. So thank you for pulling me up on that.
One additional question was Edward was wondering if you could maybe just quickly go through how to read the syntax of the data type definition.
Yes. Shall I do it with? I wonder if I have a better one than. No, we'll just use this one. In fact, no, let's not use this one. Let's use an even simpler one. I'll dig one out of the. This is one out of the library, so I won't be able to type check this one. So if you're familiar with Haskell, in Haskell you would write a data declaration in this sort of form, where you just give the constructor names and then you give the types of the arguments to that constructor. And a type declaration like that in Haskell would generate two names. It would generate the name Z, which has type nat, and the name S, which has type nat arrow nat. So this syntax for declaring types, we are giving directly the types of each of the data constructors. So the data constructors are the most primitive form that a data type can be. So it's like the canonical values of that data type. I'll maybe show you list as well, because then you can relate list to HList. So list would look a bit like this. So nil is a list with some element, and then cons is some element, and then the tail of the list, and then that gives us a list. So HList is a list type where instead of saying every element is the same type, we say that the element types are computed by this list of types that we give it in the type. So so nil is an H list that has, well, there's nothing in the H list, so there's also nothing in the list of types in the index. And in cons, there's something of type T in the H list, and then there's an H list with some things of type T's. So the whole thing is an H list with a thing of type T and a thing of type T's. I think the short answer to the question, though, is we give the types of the constructors explicitly. So I hope that helped. Right, I'd better move on to an interesting example. I mean, I hope that they were at least a little bit interesting. I was gonna show you a real example from the actual implementation of Idris too, but it's to some extent it's more of the same. But I do want to do this example before I finally go on to how things work, because I think this is a neat example of a place where we're using dependent types to show the relationship between two data structures. So I'm implementing a run length compression on lists. So run length compression is where you have some number of copies of one thing and then some other number of copies of another thing. So if you have data, if you have a list data where there's lots of runs of things, this can work pretty well. So I think it originated in a paint program in MS-DOS in the 1980s, if I remember correctly, where you often get runs of the same pixel color. So the first thing we need to do, so let's the representation of run length encoded data. What I want to do is explain in the type that my run length encoded data is representing some other bigger list, and we'll use that bigger list to ensure that the representation is sound. We'll also use it, it turns out, to help us write a bit of the program. So an empty run length encoded list, well, that's the run length encoding of the empty list. If we have a number and a thing and a run length encoded rest of the list, then that will give us a representation of a list which is n repetitions of x and then the rest of the list. So this plus plus is the concat operator. By the way, there's nothing to stop. I chose to do this as just a sound representation rather than necessarily the most precise. So this is there's nothing to stop this number being 0, which would be a very bad run length compression. But let's not worry too much about that for the sake of this this example. Right. So when we represent some run length encoded data, so this test compressed data, it's 3 x's followed by 4 y's. I've put a question mark here for the type of this, just to show that there's a bit of type inference happens. And just occurs to me that I run through my examples before I give talks every time, and I didn't test this one. So I wonder what this is actually going to do. Oh, that's a relief. So it's oh, it's not completely evaluated it though. That's a bug in the display. But you'll see in the type that it's the run length encoding of 3 x's plus 4 y's, and it should have evaluated this, but it didn't. Never mind. Right. Oh, we do need to generate rep. Let's have rep back. Now, I'm just going to concentrate on compress because compression is a little bit fiddly. And kind of out of the scope of this talk, but you'll notice in the type of run length compression, so it's indexed by a list of things. The type kind of says what we need to do to uncompress the list, because the index of this type is the original uncompressed thing, and it sort of suggests that, well, if I've got an empty list, then the uncompression is the empty list. If I've got run, then the uncompression is n copies of x and then the rest of it. If I try saying, so I'm just going to initially, for my implement for uncompress, I'm going to say that, well, I'm uncompressing this list, this run length encoded list of x's, and I'm returning a list. So just for the first implementation, let's see what that comes up with. So I'll let you, while I take a sip of orange juice, I'll let you peer at that. So hopefully you see that this isn't quite what we want, because, well, n hasn't been used. It didn't know, that the search didn't know, like there's no hint that says you need to be using rep. So there's no real way it can guess that I need n copies of x. We've got an n here, but there's no way to guess that it, a reasonable way to guess that it needs n copies of x. And worst of all, I haven't really said anything in the type. This type doesn't say anything about the relationship between the list I'm returning and the list that's coming in. So somehow I want to say that the thing we're returning is this list x's. I want to be explicit about that. Now, one thing I could do, you might think at first, well, x's is available. Let's add a candidate definition and let's just try returning x's. Let's just blunder on and say x's was the uncompressed list. We've got it in scope. Surely that's okay. But unfortunately, it's not going to let us do that. It says x's is not accessible in this context. So this is a new thing in Idris 2, that we have quantities in types that allow you to say whether something is around at runtime or not. So in this uncompressed function, we do have x's as something that's in scope. So it is at compile time, we know that this is a run length encoding of the list x's. But, and this is a good thing, we don't have x's available immediately at runtime. If we did, we wouldn't actually have achieved anything by compressing the list. It would, because we'd be carrying around the original list as well as the compressed version of the list. So the fact that this is a 0 is a good thing. What we need to do, though, is explain to the machine that we want to construct a list. And when we finished constructing the list, that will be the list that we knew about at compile time, only we constructed at runtime. Now, if you've been looking at the code, there is a hint. There is this singleton type. So a singleton type is a way of saying the type has exactly one inhabitant. So the thing we're going to return is a type, a singleton type whose only inhabitant is the list x's. X's are the thing carried by a singleton. If you look at the type of val, there's no quantity annotation on x, so that means it's unrestricted. So this uncompressed function, it's going to take a run length encoded version of x's, where x's is only known at compile time. It's going to build a singleton representation of x's, where x's is built at runtime, and we're going to have a compile time guarantee that those two things match up. And because we've already written this, we've kind of written the uncompressed function already, just by having this run length encoded data structure with it in the type. So if I try to generate that, that's what we get. So it's so the empty list in this case. And the tricky thing it has to do is this singleton needs to be unpacked. So we need to pull out the value, and then we need to pack it up again when we get the result. But other than that, unpacking and packing it up again, we can pretty much generate it by looking at the indices here. So it's another case, and this sort of thing comes up over and over again in independently typed programming, and there's possibly more things we should do about it. But if you've explained a program in one place, you shouldn't have to write the program again in another place. And it's nice to have even relatively simple type-driven synthesis tools to avoid having to redo the work. Any questions on that one? I notice I'm not really paying attention to questions. Okay, I'll take that as a no.
I just found my unmute button.
Oh, right. Go ahead.
So I kind of wonder, why are you able to use a function which is rep in the type declaration of run?
Oh, right. So this is a question not about the synthesis, but about the type system in the first place. Is that right?
Yeah, because it makes sense that you could synthesize the program from the type, because the type actually has a program statement in it.
Right. Yeah. I mean, it's when you put it like that, it's like, well done. Of course you can do that. Which is, to be honest, it's the response I wanted. But yeah, the question is how. What does it even mean to have a function in a type? So this is an example of what I mean by first-class types. So you can put functions if a type is indexed by some data that is a value. So this run length type, it's indexed by some list. List is a value. You compute lists with functions. It's just like the ordinary list that you would see when you compile and run the program. So the fact that the thing that's expected here is a list means that we can use any of the list functions. So there's so in Idris, because there's first-class types, there is no ceremony involved in running a function at the type level. So you don't need to do a special type level version of a function. You just put it in the type. So, people talk about type level programming. I just call it programming. I think to go a bit deeper than that might involve a bit too much of a digression, but does that at least give you a suggestion of?
Yeah, no, that helps.
Yeah.
Type says first class objects that kind of helps because I'm used to programming in languages where types are different from programs. So
Right.
you can't run a function on a type.
Yeah, I mean that's as you'd expect. I mean, that's the normal way of doing it. So out of curiosity, any Haskell or Scala?
No, I'm a systems programmer. So
Oh right, okay. Yeah, okay. I'm just trying to find. I'm trying to find an example that might match up. But
right. No, I mostly write C++, which has a
Ooh,
very flexible type system, but there's a
right.
distinction between type level functions and program data level functions.
But C++ is a great example because C++ does have type level programming. It has like all sorts of exciting things you can do with templates, and I believe that the type that's part of the system is Turing complete. Is that right?
It is, yes. The C++ type system is the template system is Turing complete.
Right.
So you can actually write your entire program at compile time if you want to, but you still have to use the compile time versions of all functions. You can't write a function like rep that could either accept a type or an integer.
Right. Yeah, so you will actually be able to do all of this sort of thing in C++. It would just be a lot more involved because you have two different languages. So probably the thing to take away from this is that Idris is so noticing that people love that sort of thing in C++. It's really cool. You can do all sorts of clever things, but it's a lot harder work than I think it needs to be. So one of the things we're trying to achieve with Idris is making the kind of trickery you do with C++ templates just something that's natural in the language. Yeah.
No, and it's true. You spend a lot of time in C++ sort of writing two versions of a function: the template one for at compile time and the runtime function for data. You know, there's
yes, absolutely.
There's the template edition and there's regular edition, and there's template, list cons, and there's regular list operations.
Right, and in fact, I'm going to give that as the takeaway for this talk is first class types make doing all of these fancy things just natural. Like we don't have to. You don't have to say, oh, this is a bit hard. It's just a thing that you do in the language. So I'd really like to encourage people to try that sort of thing out a bit more, rather than trying to do fancy things and shoehorning them into type systems where it doesn't really work. Give it a try in Idris and see if it works out. Right, just conscious of time, I think I should probably do a quick summary of how I do have several hundred more examples, but you don't want to sit and listen to me do that all day. I will instead do a little bit of an overview of how this works, and I'm maybe given a little bit of a hint as to how things work already, but just to make it a bit more precise. I do want to be clear that there is no magic, and sometimes I give these talks, and I look at mentions on Twitter or whatever afterwards, and people are saying things like, "Whoa, that's magical," and it's really not magical. It's in fact, one criticism I've had of this approach to programming is, oh, it's just a conjuring trick, and that kind of is just a conjuring trick. There's a little secret underneath, like all the good magic tricks or conjuring tricks. There's a little secret underneath that makes everything work out. So I want to give away what that is. If you know what the secret is as well, you can use it better. It's just my advisor, James McKenna, when I was starting my PhD, and I was really struggling to do kind of interactive proofs, that sort of thing, sort of the fundamentals of type theory. He would implore me to be the machine. He would say, try to understand the mechanics of what's going on inside the machine, and then you will understand the process of programming it. So what I'm saying here is learn to be the machine. So the essential idea is it's a type-driven search. We don't generate all of the possible programs and then see which type checks. We build programs incrementally. So I showed you holes, and I showed you case splitting. So the machinery that the program search is using is that machinery. It is exactly that machinery that's used for interactive editing by anyone else. So one thing that we're trying to do really is come up with a semantics for what the interactive editing process is. So what are the primitive actions, so that you can start writing combinators, functional style combinators that that glue those actions together, and you can write your own. You can write your own proof search mechanism. So actually, what I want to do is this thing that is implemented as part of the IDRIS system. I would like to be able to implement it as a kind of a reflection mechanism. So that I would like the program search to not even be implemented in the IDRIS core. I'd like it to be something that's implementable as a library, which I think is achievable. Anyway, essentially it's type-driven search. Build programs incrementally. It doesn't stop when it finds the first result. It will give you a result and how to continue the search. So it'll take a batch of results, and then by some heuristic, it will then order them. So if you have some primitive features in your language core, then you can probably just implement this with not too much work. You know, hesitate to say that something is a small matter of programming, because you know there are details. There's a bit of a draw the rest of the owl involved here. But there are some primitive. The primitive operations you need are holes for saying, you know, partial search results are incomplete, so we need to generate partial results and then explore inside the hole. Unification, because when we're checking, when we're testing a constructor against a type, we will unify the type of the constructor with the expected type, and that will give us a bit more of the solution. So that will solve a bit more of our program, and it will cut down the search space. And then case splitting. This is for if you find that a search hasn't achieved anything, maybe splitting one of the inputs, maybe a pattern match on one of the inputs will work. So having case splitting as part of your system could potentially help there. And yeah, we don't need these details. In fact, no. What I'll do, I'll run through an example. That's maybe a good way to finish, because if I run through an example, then you'll see the outline absolutely in action. So I did say that Vect was the tired example, and try as I might, I couldn't come up with one that I mean, tired as it is, it's really useful because it has some nice characteristics. It's very simple. So vects, if you haven't seen them before, they are lists that are indexed by the length. So nil is a vect with 0 elements, and cons is a vect with successor of something elements. So it's nice. It's a nice example for program search because it cuts down the search space. So this search hole, if we look at the context of this hole, we've got a few things available. We've got our X, which has type A. We've got our X's, which is K things long. We've got Y's, which is M things long. And we're trying to make something which is successor of something long. So the successor thing is crucial here. So show the outline of the algorithm. It's try a few things in order. So try the local variables. If it's a function type, refine it with a lambda. If it's a data type, go through the constructors, see which ones unify. If nothing else works, try making a recursive call, but when you make the recursive call, make sure you're getting closer to the base case. So in this case, the only thing that's going to have any hope of working is a cons. So if we go through, like none of the things in scope fit the type. Cons does fit the type. Cons has type, the return type is vect of some successor of something. So the next step is we have a cons, and there are 2 subholes. There are two arguments to cons. So we just work through the arguments. So what is so A1 has type A. We have a local variable of type A, so we'll just pick it. A2, well, we don't have any local variables that work. Neither nil or cons immediately work. So 0 doesn't unify with K plus M. Successor doesn't unify with K plus M. We need to know more to be able to do that. So the only thing that will even allow us to make progress here is to make a recursive call. So we'll do that. Making a recursive call. So we check for, so we build the recursive call, and it's only after that that we check that it's a descending recursive call. So now A3, that's generated 2 cases. So A3, that just works. We've got an X's. A4, oh, that's supposed to be an M. Sorry. A4, we've immediately got a Y's. There's no more holes. We're done. So it is literally doing exactly what I do when I'm writing these programs. It's just doing it a little bit more incrementally. Now, oh, I noticed that I'm running out of time, so I'm just going to say that program search is it's expression search plus you do a case split if it didn't work. So if expression search doesn't work, do a case split, try an expression search on everything that you've generated up to a reasonable maximum depth. This is my second last slide, if I remember rightly. So this happens inside a search monad. The search monad gives us the result that we found. It also gives us a continuation that says what to do if the current search is considered unacceptable. So unacceptable would be either, well, it didn't work, there was an error, or it might be the user has hit it with a hammer. So I'll give me the next result hammer. So user can always ask for the next result. The heuristic I suggested, which that's a very interesting question about rep, why doesn't it find a different rep first, which I'm going to investigate, probably on Monday now, because it's Friday evening where I am, but it's certainly something I'm going to investigate. But this heuristic of ordering by the most local variables turns out to be a really nice heuristic, and a lot of the time gives us the definition that we actually wanted. So refinement I'm not going to talk about. Really ought to mention related work. As I said earlier, a lot of people are working on this sort of thing. I've just picked a couple of examples. For all I know, there are people in the audience who are working on these systems, in which case I'd love to talk to you. Maybe not now, but when we can find the time, I'd love to talk to people who know more about how synthesis works for other kinds of type systems and see if there are ideas that we can share. Right, I will stop there because I see we're at 2 p.m. In Georgia. The way I like to finish is just to say that if you have the right primitives in your language, so if you have the holes, if you have the case splitting primitive, and if you have unification, turns out that program search is surprisingly simple to implement. I'm always very wary of this word simple, but you know, having implemented the machinery, it was the work of like 2 or 3 days to glue it all together, because it was a matter of taking the primitives, the right combinators, and seeing what came out. So it was very pleasing to see things like rep coming out, things like append coming out. A couple of examples I didn't show you was a call CC, so I can find call CC just by the program search. It was very pleasing because I don't believe I could ever write call CC on my own. So I'd be lying if I claimed I could understand call CC. Lots of possible lines of work. Domain-specific synthesis. Something I'm looking at is communication protocols, session types for communication protocols, and being able to say to the machine. And this actually came up earlier when talking about hints. It would be nice to be able to say to the machine, do some program synthesis, but use this fragment of the search space. So give me the next action in a protocol, for example. Give me the next operation on that channel. So things that are immediate from the type, but you have to tell the machine which particular search algorithm to use. And I mentioned machine learning because someone always asks, "Can machine learning help?" And I don't actually know the answer. I need to know more about machine learning. Again, maybe one of you knows more about that, and that's something we could explore. Anyway, that seems like a good time for me to stop. Thank you very much for listening, and thank you for the interesting questions. It's very refreshing to have an audience that is interacting. It's rather hard in this environment that we're currently working in. So I have to thank you for being a very interactive audience. Yeah, thank you.
Thank you, Edwin. It was a great talk. I'm happy to see these cool examples, especially I thought the run length encoding was really cool example. One thing I wanted to is Dominic and his student Jack have recently published a paper about doing synthesis in granule using making use of the quantitative types. And I know you have some or quantitative types in Idris too. This might be something that you might capitalize on as well.
So that's an interesting question, actually. So I knew that they were working on that, and I didn't know that there was a paper yet. So do you know where that was published?
Yeah, it was in Lobster 2020. If you go to the Granule research page.
Right, I will take a look. Yeah, no, I knew that that Dominic and I've forgotten the student's name. Sorry, Jack. Yeah, so I knew they were working on it, but I didn't know how far they got. But a really interesting point about quantities. So what I used to use as an example of synthesis was take the append function and say in the type that we want to use these two arguments. So I would show generating append, and then it would generate append with the empty list. It would just say it's the empty list.
Right. Yeah.
And then I tried this heuristic, and suddenly I didn't have an example anymore that showed the value of the quantities. So I don't currently have an example where quantities matter. So I definitely have to look at Jack and Dominic's paper, because
they have a number of examples.
maybe they have some.
Yeah.
And yeah, granule's really cool, because the quantities in granule, they express a lot more than the quantities in Idris, but it's sort of, in some ways it's more expressive in the resource, in talking about resources, maybe slightly less expressive in the kinds of things that you can put in types. So something that combined the powers of granule and Idris, that would be our plan to take over the world, I believe.
Well, I have 2 papers for you, so.
Fantastic.
Does anyone else have any last minute questions before we adjourn? Looks like there's a few questions on YouTube, if you don't mind.
Yeah, let's go for it. I'm happy to sit here for a little bit longer.
So Dennis asked, singleton X's is a good example of structural bounded type, comparing to taking the subset of a list.
Okay.
Similar to finite sets, comparing. It's hard to kind of read it, honestly. There's a little code there, so.
Yeah.
So the question is, so they've rephrased it here. So the question is, any ideas what a synthesis will work for non-structural types?
So what would be an example of a non-structural type? Would it be like that sort of thing of saying a list plus an ordering proof or something like that?
Right. Yeah. I think that's what it is.
I don't know. I've thought about it a tiny bit, because something I'd like to be able to do. I mean, this isn't quite answering the question. But it is related to something I want to be able to do, which is, I mean, proofs are programs in my world. So we have proofs of properties of functions, and sometimes those proofs are structural things. So it could be that if you're generating, so if it's a list and the predicate, then the list part is structural, but the predicate is kind of constraining what the list could be. So it becomes still structural but quite complicated problem, and this might be a thing where we need to give a few more hints to the proof search machinery. So if you can come up with some way of encoding appropriate hints, then maybe you have half a chance. But I don't immediately know if it would work well. I'm wondering if it's also, it reminds me of another thing that's potentially interesting, which is not only type-driven synthesis, but example-driven synthesis, where you could maybe use an example to constrain the search space. So if you find an answer, but one of the example inputs you've given at some point isn't going to work, then could also be a way of constraining the search space. So yeah, if you have something that isn't structural, maybe it's a way of constraining the search space, but I don't immediately know how to build it into the algorithm we've got.
Thank you. Christopher League is saying in the chat that they found it interesting that in the append base case, it correctly used the local variable, but in the rep base case, it ignores the variable.
Yeah, hang on, where is that one? Oh no, that one. I was curious about that one, because if I keep, I'll probably have to start again because it'll have forgotten the state. I wonder how long we have to go before it does that. Because I did wonder about this. I felt that oops.
It chose the empty program there.
Yeah, and that meant it because I pressed a button, it forgot the state. I think it might be that implementation isn't in the initial batch of 16. Oh, there's oh, I've got to, this interface is not slick.
It's kind of like when you try to do Unicode in Agda and you accidentally hit the wrong key.
Yeah, I just noticed that it came up with it eventually got to the one that just makes the recursive call. Yeah, so that's the one that it used to generate first. It's in some interesting orderings that it's picked.
Yeah.
But
there it is.
Did it come up?
Well, that's the one that we might expect first. I don't think we've seen one using using X in the base case yet. I think.
But if I understand correctly, there's no connection between the two parameters, right? It's not choosing or between the return and the 0, right? It's not because there's a natural base case that we're generating an empty list or something like that.
Yeah, well, I think it might just be that the order that it's exploring things is that anything interesting in the base case just comes up too late in the search order.
Yeah.
So it's explored that bit of the base case, and then now it's exploring more of the recursive case, and it's going to have to finish exploring the recursive case. Oh, here we are. It started doing something interesting.
Yeah.
Going in the wrong direction.
Yes.
Case.
My guess would be this is to do with the size of batches that it's generating. Anything else. So, once you move from algorithm into heuristic, then good luck.
Thanks.
Also, it's also a function of the way the Vim mode works is it has to do the whole explore. Like there's no state between the editor and Vim, which is a bit of a pain. So it actually has to do when I ask for the next definition. So it generates 1 and shows me the first, then it generates 2 and shows me the second. So the editor protocol is cleverer than that, but the Vim mode is not. So also worth noting that the short pause you see between generating definitions, that's almost entirely because it has to start up the scheme runtime system. So every time it has to restart Idris compiles via scheme. There's about a 0.3 second startup cost. So the search itself is actually quite quick, and this little pause is just Shea scheme spinning up.
And so every time you have to call out to Idris, it's basically a new process every time it restarts.
Yeah. This is only in the Vim mode. Other editors are a bit more sophisticated than this.
Yeah.
It's I'm sure people notice that little pause, but I feel like I should at least explain the little pause.
I mean, yeah,
I completely our fault.
Time to do the search personally.
Yeah.
So yeah, cool.
Yeah, and in practice, in terms of how long the search takes, I need to put a timeout in, but I've generally found that if it doesn't find an answer within a second, it's never going to find an answer.
Ah, interesting.
But then, I kind of stopped working on this when semester started, so I'll get back to it and explore these things more. I'm sure we all have the same.
I have one more if you have another minute.
Yeah, go on.
I wonder if you've thought about integrating this with some small unit testing or quick check type of things so that you can eliminate candidates that don't pass tests in addition to the types.
Yeah, I think we should do that. I don't quite know how it would work, as in what the notation would be, but maybe a way of giving examples, which are, and those examples could be either quick check style properties, or they could simply be example inputs and outputs of the sort you would see in unit tests. Then we'd have to think about how do we integrate with that that with the search so that we prune the search early. So I don't want to generate a complete definition and then check it against the example, because then we haven't necessarily saved anything.
Right.
So we should be able to do that, because it's a necessary feature of a dependently typed language is partial evaluation. So we could partially evaluate we could take our partial definition, partially evaluate it against an example, and it might be that you encounter an error really early. So I think that could probably work. Before I do anything there, I really need to look at what other people have done with example-driven program synthesis, because I think there's quite a bit of work on that. But the more information we can give it, the better.
Yeah.
It's a question of how well it fits into the workflow of this type-driven development, but sometimes giving examples will be the right thing to do, I'm sure.
Cool. Well, thanks again, Edwin. This was really great.
Yeah, well, thank you for having me.
Yeah.
And for me, it is now very much beer o'clock, so I'm going straight to the fridge when
Yeah.
I close down the room.
Enjoy. Thanks everyone for coming, and this was recorded and will be posted on YouTube. I'll post it on Twitter. If anybody wants the link, they can just go back to the same talk website, and it'll be on there.
Bye, everyone. Have a nice weekend.
Okay, thank you.
All right, good night.
Everyone.
Thanks.
Yeah, thanks, Christopher.
Yep.
I usually wait till everybody leaves in
We'll
case.
just have a quick skim of the chat before I go.
Yeah, sure.
See if I missed anything. I think you pretty much said all of that.
Yeah.
Great. Right, I'll be off.
Yeah, thanks a lot.
Cheerio, and enjoy the rest of your day.
Yeah. I'll send you a couple papers on graded dependent types.
Oh yes, right, absolutely. That would be great, because I'm sure there's stuff that I've while I've been in my teaching JavaScript whole. I'm sure there's interesting things that have been happening that I've missed. So I'd love to hear about them.
Yeah, Stephanie Wyrick and I have, and Richard Eisenberg, first one of Stephanie's students, got a pop-up paper, and then me and Dom, our paper, which I think you've heard about before, is getting at ESOP, but it's on archives like this.
Oh, Popple, that's awesome! Congratulations on that.
Yeah, thanks. My first ever one, so I'm pretty excited.
Yeah, I'm very good at getting rejected by Popple.
Yeah, same here.
Who isn't?
Yeah, I like getting rejected every time, so I was like, finally a win. And in 2020, no less, made my year a little bit better.
Yeah, absolutely. Right.
Cool. Thank you again.
Yeah.
Cheers.